Hello, AP Calculus and Calculus students. Today is November 24th, 2022, and this video would be kind of like part two to what you guys had learned about implicit differentiation in calculus. Specifically today would be about related rates of change. So these problems are using implicit differentiation to solve, everyday real world problems like physics problems or business problems. So let's begin, shall we? Related rates of change. So some problems in calculus require finding the rate of change, or should we say two or more variables that are related to a common variable. Usually in a lot of these problems, that variable would be time, t for time. And to solve these kind of problems, we need to find the appropriate rate of change by using implicit differentiation, and then do that with respect to the variable t or time. Now, a given rate of change is going to be a positive value if the dependent variable increases with respect to time, and negative if the dependent variable decreases with respect to time. Just like we were doing on a normal XY graph, all right? And those of you who know independent dependent variables from science or physics, then you should understand that by now. Now, the sign of the rate of change of the solution variable with respect to time will also indicate whether the variable is increasing or decreasing with respect to time. Now, I want to point out that by this point, though, before you start doing these related rates of change problems, you should be good enough with implicit differentiation by now, okay? So it should not be difficult for you at this point to be able to take the derivative of both sides of something, okay? But now we are going to do that with respect to t, okay? So we'll be able to see how x and y can vary with respect to time t. So first example, number one, air is being pumped into a spherical balloon such that its radius increases at a rate of 0.75 inch per minute, okay? Find the rate of change of its volume when the radius is 5 inches. So this is kind of a implicit differentiation applied to physics problem, So first thing I do is deal with the basic equations that I need. I'm dealing with a sphere, right? So you remember the volume of a sphere from geometry, okay? If the sphere has a radius of r, the equation is its volume equals 4/3 times pi times the radius to the power of 3. And if you differentiate that with respect to t, so we'll say that that is called dv over dt. That would be equal then to 4/3 pi, okay? So those are treated like a constant. 4/3 and pi are both a constant, so it just stays in front. Then this 3 will come down, and that would be r to the power of 3 less by 1. So that's 3 minus 1, which is 2. That's where we get 3r2 from. And then, because I took the derivative of that r, okay, with respect to time, I have to also multiply that by dr over dt, okay? I'm respecting both these variables, right? Volume, and also the radius. Both variables in this equation are taking the derivative of with respect to time. And that's why you get a dv over dt and dr over dt. And so we'll simplify that, okay? 3's cancel out. You would just get 4 pi r squared. And you still have these guys left, okay? And so they said that the rate of change of the radius, dr over dt, is equal to 0.75 inch per minute because the radius is increasing with respect to time. So at r equal 5 inches, which was provided to you, right? Don't forget the information you were given. So going back here, at r equal 5 inches, you may go ahead and plug that value into the derivative that we just got. That's from the previous page. We had 4 pi r squared times dr over dt. So substitute the r value they gave you here and the change of the radius with respect to time. That's the dr over dt equal 0.75 inch per minute. So that will go in for dr over dt. Right, so now you can get everything and you can get the change of the volume with respect to time. And then if you don't, take the value of pi equal 3.14, you just get 75 pi, okay, inches to the power of 3. That's cubic inches per minute. Okay. So that is one example of implicit differentiation used with, actually geometry and physics. So to interpret what this means, the volume then is therefore increasing at a rate of 75 pi inch to the power of 3 per minute when the radius of the sphere has a length of 5 inches. Okay, so next part here, sorry, this is so in the way. Now a car is traveling north towards an intersection at a rate or speed of 60 miles per hour. Yeah, it's a very American unit. While a truck is traveling east away from that intersection at a rate of 50 miles per hour. Find the rate of change of the distance between the car and truck when the car is 3 miles south of the intersection and the truck is 4 miles east of the intersection. Okay, so that is the given problem. We have quite a few values given to you here. And let's see if we can move that somewhere else. Hopefully you can see it. Okay, car traveling toward the intersection at a rate of 60 miles per hour, blah, blah, blah. All right, so let us define some variables here. Let's call X distance traveled by the truck, okay? And the Y will be then the distance traveled by the car. So two different distances here. You could call them A or B if you want, but any letters would do. Z would be distance between the car and the truck, right? So now I have the X, Y, and Z. And now, if I want to treat this like a right triangle, if you want to imagine this picture here at this intersection with a right triangle, then I can use Pythagorean theorem. Okay, so x squared plus y squared equals z squared. That is shown kind of like this. Okay, so this is how I show the distinction between, how far the car is from the intersection, how far is the truck from the intersection. Remember, x is by the truck from the east way, y is distance traveled by the car, so that's shown right here. And then z, right, is distance between car and truck, got it? And that's why we're forming a right triangle here around the origin. Anyhow, I can use the Pythagorean theorem for this right triangle, okay? And so now we are also given this other information. They said that the rate of change of the truck, okay, is dx over dt, 50 miles per hour. That's that truck speed, okay? And it's going, of course, away east from the intersection. But the rate of change for the car is dy over dt, okay? So it will be having a different sign, or at least compared to the truck. So it will be going in the vertical direction, but it's going towards the intersection instead of away. So I would just give that a negative 60 miles per hour if the truck is 50 miles per hour. Okay, positive. But if you had the truck negative 50, make sure that the car would be 60 miles per hour. So one or the other, okay? But I'll just keep it like this for now. Now, let's differentiate with respect to time over dt. So the equation of Pythagorean theorem here, I have all the three variables here in this equation. So I will take the implicit differentiation of it from both sides. So, and that becomes 2x times dy over dt plus also 2y dy over dt. And then the other right side, 2z dz over dt. Okay. Then we can obviously, get rid of 2 from all of them, right? Because 2, if I factor it out on the left side, will cancel with 2 on the right side. So all the 2's will go away, or the whole thing is just 1, 1, 1 for coefficient in front of the x, y, and z. All right, so again, that's what you get after I factor out 2 and cancel out the 2. Now I have here, I can put in the values, the rest of the values given to us from the problem, okay? So if you look back at the very beginning, right? We know the truck is 4 miles east of the intersection. and the car is 3 miles south of the intersection. So we have 3 and 4 given there. We have the individual speeds. So put them back into your derivative. Like this, okay, 4 miles times 50 miles per hour, and then plus 3 miles times negative 60. So this part here is the truck, this part here is the car, okay? And here is that, then, let's see, distance between, yeah, we have to find the intersection. Okay, you guys, before you do that, you have X and Y. So you should be able to find Z, correct? So Z, as you know, if you did the Pythagorean theorem, so when you did the Pythagorean theorem, which we didn't really do like anywhere here, but you could do it, put in the X and Y value in here, and it's a right triangle. So you should be able to find Z. And that Z would be then 5, all right? So that's where we get this 5 from. It's a 4 and a 3 for the legs of the, triangle. So that means the hypotenuse would be 5. But then dz with dt would be left like unsolved. So multiply all that out and then isolate dz with dt. And so you get that is 4 miles per hour, okay? So what that means is the distance between the car and the truck is increasing at a rate of 4 miles per hour at the time in question. Got it? Okay, all right, guys. So that would be then your first 2 examples of the related rates of change. This would be a section of the implicit differentiation chapter that will be on for a while, a few lessons. So I will send you another video to give you more examples in this. Okay, this is just 2 examples for you so you know how to use them so far. All right, that's all for today, guys, and see you later in class. Bye.